Hello everyone, in this video we are going to start study about an interesting data structure known as trees. Till now you might have heard about data structures like arrays, linked lists, stacks and so on. These data structures are linear data structures. For example, take a linked list. In linked list you have a set of nodes where each node points to the very next node. In this linked list, suppose there are 3 nodes. Let us say this node stores the data 4, this stores 1, this stores 8, and this is an end pointer. What is the start of this linked list? Correct. This node points to the start of the linked list. As you see that in a linked list, there is a logical start, there is a logical end pointer, and also there is a logical meaning of the next element. These are the properties of linear data structures. What is a data structure basically? Data structure is nothing but a way to store and organize data in a computer system. How will you choose which data structure is perfect for a particular problem? You might choose this based upon some different kinds of criteria. The first criteria might be the type of data that you are representing. The other decision might be to reduce cost or time complexity for frequent operations. Example, suppose you are given a problem that hey, we are given a set of numbers and multiple queries where you have to find if a particular number exists in the array or not. What data structure you will use? You can use an sorted array and apply binary search, or you might also use a hash map. Sometimes the choice of data structure is based upon reducing space complexity. Tree is a data structure that is most suited for hierarchical type of data. Consider the organizational hierarchy of a big corporation. There is a CEO. Under the CEO, there might be multiple presidents. Similarly, under each president, there might be multiple vice presidents, and so on. This is a type of data that is one of the most common types of data that can be represented using a tree. Why is it even called a tree, by the way? There is a very similarity between this data and an inverted tree. What are these things in the tree? Yes, these are the leaves. Similarly, in a tree data structure, the end nodes, had there been no other nodes downside it, are known as leaves. What is this in the tree? This is a root. Similarly, the top of the tree data structure is also known as the root of the tree. So basically, a tree data structure represents an inverted tree. Now, let us look at some terminology related to trees. Let me draw a formal tree for an example, and let me number the nodes in some way. 1, 2, 3, 4, 5, 6, 7, 8, 9. The very first terminology that is related to tree is the root of the tree. The root of the tree is nothing but the node which is at the very top of the tree, or the node under which all the other nodes of the tree lie. So in this example, 1 is the root of the tree. Now let us discuss the parent-child relationship. As there is an edge from 7 to 9, 7 is known as the parent of 9. Similarly, 9 is a child of 7. Now, what is the case of 6 and 7? As 6 and 7 have the same parent tree, 6 and 7 are known as siblings. Okay. Now, the very common term that you will see when reading about tree algorithms is a leaf. A leaf is a node that has no child. So, in this example, node 8, node 5, node 6 and node 9 are leaves of the tree because They have no child of themselves. Now consider a path from the root of the tree, that is 1, to a particular node, for example 8. We see that on this path the nodes that lie are 1, 2, 4 and 8. If a node lies on the path from root to a particular node, for example 2 lies on the path from 1 to 8, 2 is an ancestor of 8. Conversely, 8 is descendant of 2. Now we studied about ancestor and descendant. Now let us see for a particular node 8 again. What is the length of the path from 1, that is root, to 8? As we do here, the length of the path from 1 to 8 is 3. The length of the path from root to a particular node is known as depth of a node. In this case, the depth of node 8 is 3. Similarly, what is the depth of node 3? As the length of path from 1, that is root, to 3 is only 1, which means depth of 3 is 1. Similar to depth, there is another term which is height. People tend to confuse between depth and height. As depth is the length of the path from root to a node, height is the length of path from node to farthest leaf in the subtree rooted at node. Let us take the example of node 3. In node 3, what is the subtree rooted at node 3? Correct. This is the subtree that is rooted at node 3. What is the farthest leaf from 3? As you can see that the farthest leaf from 3 is the node 9. So, what is the length of the path from 3 to 9? It is 3, 7, 9. So, the length of path is 2, which means height of node 3 is 2. So, make sure you understand the difference between height and depth clearly and don't confuse between those. This was the definition of height of a particular node. Now, what is the height of the tree? Height of the tree is nothing but the height of root node. So, in the example above, what is the height of the root node? Clearly, the longest leaf from the root 1 is 8 or 9. What is the length of the path from 1 to 8? As we saw earlier, it is 3. Thus, the height of tree in the above example is 3. Great. So, we have till now discussed some of the terminologies related to trees. Let us discuss a few properties of the trees as well. The very first property of a tree is that a tree with n nodes has n minus 1 edges. Why do you think that is the case? Let us go back to the tree that we draw above. We see that for all the nodes other than the root node, there is an edge pointing to the node. For example, for the case of node 2, there is one edge that is pointing to the 2. Similarly, for node 4, also there is only one edge pointing to the node 4. Similarly, for node 5 and all other nodes. So, we see that there is one edge from to any node other than the root. So, for n nodes, all nodes other than root have an edge pointing to them. This means there are n minus 1 edges. Based upon the properties of the trees, different types of trees are also defined. So, for example, if all the nodes of a tree have less than or equal to 2 children, this means the tree is a binary tree. Extending this thing, if all the nodes of the tree have less than or equal to n children, implies that the tree is an n-ary tree. Let us take an example. Do you think this particular tree is a binary tree? No, this tree is not a binary tree because we see one node has 3 children. Implies that not binary. Do you think this is a ternary tree? Ternary is also known as 3-array, we see that this node has 3 children, this node has 1, and all other nodes have 0 childs. As we see that all the nodes in the tree have less than or equal to 3 children, this means that this is a ternary tree. Similarly, there are many other properties of the trees of different kinds of trees. For example, there is a binary search tree. We will discuss this in depth in a future video, but as an overview, a binary search tree has a property that all nodes in left subtree of a node have values less than the node value, and all nodes in right subtree have values greater than the node value. Now let us move to some of the applications of this tree data structure. A tree data structure is a very important data structure and is used in many real-life applications. As we discussed earlier, the tree data structure is the by default data structure for hierarchical type of data. So it is used in applications that resemble hierarchical data. Example, the file system of your computer. How is a file system like? There is a parent directory, or which is also known as the root directory. Inside this root directory, you might have multiple other directories and files. For example, this is a directory D1, D2. This might be a file F1. Similarly, there might be another directory D3. Each of those directories can in turn have other directories under them or files. For example, suppose D1 has one more directory inside it and 2 files. A file cannot have anything inside it, so file in a file system will be a leaf node. There might be a directory, for example in this case D2, that might not have anything inside it, which can be an empty directory. I hope it is clear as to why tree data structure is one of the best data structures to represent your file system. The second application of tree data structure is by different types of trees that exist. For example, there is a tree known as trie. Trie is a data structure that is very good to represent dictionary. It allows us to search if a word of length m exists in the dictionary in order of m time. We will study trie in depth in one of our future videos. Similarly, as I talked briefly before, there is a type of tree known as binary search tree. Binary search tree allows us to find if a data exists in the node, exists in the tree in order of height of the tree. That is why you will see that height of the tree is very important factor in analyzing the complexity of tree algorithms, and we will study it in depth also in future videos. One last application of tree that is commonly used is in routing protocols and internet. Are you guys aware of a DNS? A DNS is represented like a tree. Suppose you have to find the address of www.google.com. A DNS server is organized like a tree. There is a root domain dot, inside under which there is a .com, under which there will be a .google, under which there will be www. Similarly, suppose it had to represent facebook.com as well. To represent facebook.com, the root domain will remain the same, .com will also remain the same, but there will be another Facebook here. Great. I hope it is clear as to how a DNS server might now be resolving your queries.
Myself Robin, and we will solve some of the simple questions of tree today. Let's solve some basic questions today. Let's start with the simplest question with the binary trees. Now we have been given a binary tree and we need to figure out whether that given tree is height balanced or not. Okay, what is the definition of height balanced binary tree? It is defined as a binary tree in which the depth of two subtrees of every node never differ by more than one. Okay, I need to return 0 or 1 for this problem. I need to return 0 if my tree is not balanced, and I need to return 1 if the given binary tree is balanced. This is the input that is being given to me, and I need to figure out whether the given binary tree is balanced or not. Okay, as we can see that the height of the left subtree here is just 1, as well as the height of right subtree is also equal to 1. It means that, okay, the difference between the heights for the left and right subtree, it's equal to 0. Okay, if it is 0, that means it is less than 1. So the answer for this case, it should be true. Okay, fine, nice. Now if I just visualize this input, in this input, as we can see that in the left side we have two nodes, but in the right side we don't have any node. It means that, okay, the height in the left subtree, it's equal to 2, but the height of the right subtree is 0. So if I take a difference, then the difference for this as a rule, it's equal to 2 minus 0, which is 2. And as it is greater than 1, so that means I need to return false or 0 in this case. Okay, now we got the question. Okay, now let's try to visualize how we can solve this question. Okay, the question is, we have been given a binary tree. Let's say this is the binary tree that is being given to us, and we need to figure out whether that given binary tree is balanced or not. Okay, the simplest thing is kind of a really simple question, that what we can do in this case, I need to first check if that given binary is balanced or not. That means that first of all, the left subtree also should be balanced, as well as right subtree also should be balanced. That should be true. If both the things are true, and if I just calculate the height of the left subtree as well as the height of the right subtree, if I figure out height of both the subtrees, then the difference should be less than equal to. If these three cases are true, that means I can say that, okay, that given tree is height balanced. Okay, now if I need to do that, in order to solve for my complete tree, whether that complete tree is height balanced or not, what I need to do, I need to check for my left subtree whether my left subtree is height balanced or not, or as well as my right subtree is height balanced or not. And again, when I just reached at my left subtree, and again I will check whether the left child of left subtree, the left subtree of the left subtree, it's balanced or not. Similarly, I will check for the right side, and for here as well, I will check for both the sides. So it seems to me kind of a recursive approach, in which the way I can solve this question, if I build some sort of recursion. Okay, I need also some sort of information which will help me to evaluate the height in the left side as well as in the right side. Simplest approach that is coming to my mind is, what I can do, I can make a function, pass the root, and check whether the left side is balanced or not, or also check whether the right side is balanced or not, and somehow evaluate the height for the left side and evaluate the height for the right side as well, and then just check the difference. And if this gives true, this gives true, and height is less than equal to 1, in that case I will return true. In other case I will return false. If I just apply that algorithm, that will give me the answer. But now let's try to analyze the complexity of it. Okay, I'm doing some sort of one traversal over the tree, which will cover my recursion part, and also I'm evaluating the heights. Okay, if I will evaluate the height, that means if I am at some node, I need to traverse each level if I want to figure out the height of the given tree. Okay, again, that can go up to order of n, and at each step I am just figuring out the height. So the complexity in, if I solve by this algorithm, will be order of n square. Okay, can I do better? Okay, if I want to do better, That means I want to somehow pre-store the height information. Okay. So one approach that is coming to my mind, that what we can do, first evaluate the height of every node. Okay, but then it will take off an extra space. Okay, though. So two solutions comes to us. One of them gives us solves our question in order of n time, order of n square time, and order of one space. And the other solution solves our question in order of n time and order of n space. Can we think of something better? Okay, such that we can solve this question in order of n time and order of one space. Okay, let's try to think first. Okay, the point is, just we need to check one thing only, and that thing is basically the difference between the heights of left and right subtrees. Okay, and if I check this information at each level and at for each node, and each node just give me the answer, the difference less than equal to 2, then I am damn sure that that given tree is height balanced. So what's one thing that is coming to my mind, that forget about this thing, just try to solve in such a way I can just figure out the heights, because I know that if I want to figure out the height of a tree, it will be, I need to figure out the height of my left subtree as well as I need to figure out the height of my right subtree. So if that is the case, and the height of this will be, because anyways, if I want to calculate the height of a tree, I want to evaluate the height of the left and right subtrees. So the whole recursion part, it can also be covered here. So one thing that I can do, I just evaluate the height of every node, because if I want to evaluate the height of every node, I am checking this condition. I'm doing this thing. So, and I can check whether the difference is less than equal to 1. If it is, that means I am done. That means, okay, if it is greater than 1, that means I just found a node such that that node is not height balanced. If a particular subtree of a given tree is not height balanced, that means I can't say that the whole tree is height balanced. That means the whole tree is also not height balanced. Fine. So I can, the one thing that is coming to my mind, that what I can do, I can keep a one global variable which just track this information. And if I just solve in that way, I am done. Sounds like a good solution. Okay, let's try to solve this now. So the way I think is, so let's first make a global variable is complete tree balanced, and I can initialize the value here for this global variable. It's complete tree height balanced, and I should initialize it with true. Okay, now what I can do, I can calculate the heights for each node, because I know that while I'm calculating the height, I can check the overall height balancing thing. Let's calculate the heights. Let's say first for A, and it should return me integer value. So let's calculate height for a given tree node. This is the case. Now if A, let's try to handle the edge case. If we don't have A, then I need to return 0. Otherwise, the left subtree height, if I need to evaluate, then I need to calculate left height. Again, that function with the left node. If I want to evaluate right subtree height, same function with the right side. I need to follow this procedure, and now I can check this thing. If the difference between left subtree height and right subtree height is less than equal, is greater than 1, that means I'm done. I just found a node, or I found a subtree in more specific sense, that is not balanced. So I can change my global variable is complete tree height balance or not to value false. Nice. If I do in that way, I can surely achieve something, and I need to return the height of that given tree, which will be equal to max of left subtree height or right subtree height plus 1. Nice. If I just solve in that case, and I can return that global variable, because if it is true, I need to return integer. I just need to check if it's complete tree height balanced. I need to return 1, else I need to return 0. That is it. Let me check. I just created a global variable is complete tree height balanced. Okay, now I'm checking the height, calculating the height. The left subtree height is I'm calling the same recursive function again. And for calculating the right subtree height, again I'm calling the same recursive function again. Now I am checking whether if the difference between the left subtree height and right subtree height is greater than 1, then means I am just updating my variable. Otherwise, I am returning the max of left subtree height and plus 1, adding 1 to it, and I'm initializing it with true, and I'm calculating my height, and I'm done. Nice. Let's submit my code. Nice. Oh, we already got 261 points. Nice. Let's solve some other question. Okay. He said you took some basic question. Okay, let's try to solve some good question. Let's pick this one. Okay. I don't know, but this. Okay. Okay. Given the in-order traversal of a Cartesian tree, and we need to construct the tree. Okay. What is Cartesian tree basically? Cartesian tree, it's basically a heap ordered binary tree where the root is greater than all the elements in the subtree. Okay, you may assume that duplicates do not exist in the tree. Okay, nice. So the thing is, we have been given a Cartesian tree, and he cleared me the definition of Cartesian tree as Cartesian tree is basically a heap ordered binary tree. Okay, if it is heap, that means whether the root contain the maximum value of the given tree, or it will contain the minimum of the given tree, and it says that the root is greater than all the elements in the subtree. That means root maintains the information that is the maximum value of that given tree. So I need to construct a tree, or I have been given in-order traversal of the tree. Okay, if somebody, or if most of you who don't know about Cartesian tree, let me briefly tell what the Cartesian tree is and all those things. Cartesian tree, it's basically the concept Cartesian tree comes because the thing is, it's a kind of BST plus heap, or in some sense we can also call this tree as tree. And the way we have the definition that we have been given a Cartesian tree in that form. That is we have been given the in-order part of it, because we know that if the given tree is BST, we can, if we have been given some order, with some specific in order. Let's say that in order is 1 2 3 4. We can construct so many binary search trees. One of the binary search tree that we can construct is simply 1 2 3 4, because in that given binary search tree, the in order is 1 2 3 4, and with the same in order we can construct so many binary search trees. The point is, so the way Cartesian tree comes, it just gives us the unique binary search tree, and that uniqueness comes because of that heap part. Because in that case, why that heap thing helps me, because the way heap we design the tree now, such that the root contains the maximum value, and it also maintains the in order part. That's the basic property of BST. Okay, let's say we have been given a tree 1 2 3 4. Let's say the maximum value is 4. So I can say that, okay, the 4 should come as a root, and the elements, let's say the elements before after 4 are, let's say the elements are 3.7, 2.8, something like that, and that is the Inorder. I know that that is the maximum value. That means that, and I need to maintain Inorder as well. So it means that all the nodes which are less, which has having a index less than 4, that means all these nodes should come into the left subtree. Why? Because I need to maintain Inorder. I know that the Inorder of a BST is left, root, right. If that is the case, that I know that the Inorder is left, root, right, it means that, okay, first I need to evaluate left and then root and then right. So I can say that the all the nodes after this node will definitely go into the right side, and all the nodes before this node will definitely go into the left side. So we have been given the Inorder of a tree, and the heap is kind of a max heap. We need to construct that tree. That is our question. The question is quite simple. Okay, let's try to first construct a tree. This question is also not too complex. The point is, we have been given the Inorder of the given tree in the form of an array. Okay, and I need to construct the tree. Fine. Okay, in this question as well, I can just somehow apply some sort of recursive approach, and in that recursive approach, what I can do, first of all, I have been given a complete vector. What I can do, I just figured out the maximum value in it. I just figured out the, let's say I just figured out the maximum value in it, maximum value in that complete vector, and I just make it as root. And now what I can do, all the, I can just now recursively call for the left side as well as recursively call for the right side. And now what I can do, I can just construct this as a tree as well, and I can mark the left child for this root as the root of the left subtree, and I mark the right child of that node as the root of the right subtree. If I just solve in that way, then I can solve this question. Now first, before jumping into the code, let's first try to analyze the complexity for this question. Okay, first what I am doing, I am just calculating the maximum value. At each instance, I am calculating the maximum value. Okay, I'm calculating the maximum value, which is of kind of order n, and I'm calculating the maximum value at each step. Let's say I have a function which gives the root, so it has a node which gives me the root of the tree when it takes a given array. Now what I need to do, first I need to find the maximum element in that given array, and then I need to call the recursive function again. Let's say the index I just got after calculating the maximum value from that given array, it's, let's say, I. So I need to call the function from the left side to the I minus 1, and that same function again with the I plus 1 to right, because this should go into the right side and this will go into the left side. And what I can do, I can mark the left as this and right as this, and I can return this. Now the complexity is the order of n, just because I am traversing over each of the nodes, over each element of the array, and also I am figuring out the maximum value in that array as well. So the overall complexity for this solution, it will go up to order of n square. Okay, so we just figured out the solution which is of order n square. Now the point is, can we solve it in a better way? That is the point. Can we solve it in a better way? One thing we just figured out that what we are doing, we are just concerned about the maximum value. Okay, and somehow I know that if that is the maximum value, and so all the nodes here are comes to the left side of it. Okay, let's say I have a sequence. Let's see the sequence. Let's see the example. Let's say we have a given sequence as 5, 4, 8, 3, 1. Okay, if we have that given sequence, what we can do now? As we can see now that we have a 5, and if we just found an element which is lesser than this element, so I can safely say that as 5 is greater than 4, that means the 4 should go to the right side of it, for sure. Okay, now if I figured out 8, now can I say anything if I figured out 8? Now I know that Okay, if I have some elements, let's now try to construct something such that we can able to solve our question in less complexity or better complexity. Now let's try to think what we can do to solve our question in a better complexity. Okay, the thing is, let's say I have 5, nice. Then I come across 4. If I come across 4, I know that 4 is less than 5. That means what I need to do, I need to make it as a right child of 5 for sure. Let's say I just do that operations as well. Let's say I just keep it as right child. Now, okay, do I need the information of 4 ahead? Will it help me in any further processing? Okay, I don't know. Let's see. Let's say I just found the value 8. If I found a value, let's say now 3. After 4, let's say I found a value 3. Now what I can do? Okay, if I found a value 3 and I know that 3 is less than 4 and 3 has a greater index, that means 3 will go into the right side of it. Okay, so I just figured out a solution. If we have been given an in-order in such way, then I just need to map as a kind of right child of that particular node. Okay, if that is the case, then I am happy. If so, that means I am just keeping the information, and the time I am getting the value which is less than the particular value, in that case I just need to mark it as a right child. Fine. If that is not the case, let's say I am just getting a value which is greater than this value. Let's say I am getting a value which is 4.8. Now, so that means what should be my structure now if this information is given? If this information is given, then I know that, okay, let's say we have 5. I know that all the elements, these are less than these, the elements I am storing here, it's kind of in reverse sorted order. So if it is greater than 3, nice. So that means all these nodes should go into the left subtree of this, because I need to maintain a heap kind of information. So this particular node should be the root for these two nodes for sure. So what I can do now, the overall structure at the end, it will be something like 5, then the right child 4.8 will come, and in the left subtree I will have 4, and I know that structure. So what I need to do now, what I am just doing now, if I am getting a value which is, let's say I am iterating over the array, if I am getting a value which is less than that particular element, then I am just making that node as a right child of it and just push that something. And if I am getting a value which is greater than this thing, then I just pop all the elements which is in this stack or some data structure, because I just said stack because it is following that property. Why? Because what we are doing, we are adding the elements in the end as well as we are removing the elements from the end. And if we follow the same procedure, somehow we will able to achieve our solution, isn't it? Does it sound good to everyone? The way I am approaching or way I am dealing this problem, if I want to achieve it in a better complexity. So the point is, if we follow the same way, we can now the complexity. Now let's try to think about the complexity. If we just try to solve in that way, the thing is, what we are doing, we are just inserting an element in the stack. If that element is lesser than the topmost element of the stack, and I'm marking it as right child of the topmost element, fine. Otherwise, if the given element that I just encountered, it's greater than the topmost element of the stack, then what I need to do, I just need to pop out some of the elements from my stack. Let's say I just popped out these two elements in that case. So the last element which I popped out, I need to keep track of that information about the last element. And I need to make the left child of that particular node as that particular element. And now the topmost element which is present in the stack, I should make that particular node as the right child of that particular node as 4.8. Because in the end, my structure should be something like this, isn't it? If my structure is something like this, only then I can say that that is maintaining some sort of heap information as well as maintaining in order as well. So if I will solve in that way, I can solve my question from order of n square to order of n. Nice. And we know that we can't solve better than this complexity. This is the best complexity that we can achieve for this particular question. Now let's try to solve this question. So as I just told you, we need a stack to maintain all this information. Let's say I created an empty stack, and okay, now let's iterate over my entire array. Let's first keep n as size. Now what I can do, as I know that, okay, let's first check the big edge cases. Let's say if my stack is empty. If my stack is empty, that means I don't have any elements in my current stack. That means that the particular element should be the root. Should be the root. Or if that is the case, or okay, let's first create a root. So that means in that case, let's say my root will be new tree node, and I have been provided a constructor in which I can just pass the value of integer and it will create a node. So I just need that value, which is a of I. Nice. And kind of I'm done. Okay, now I figured out the root, and it's better to maintain a stack of tree node. So I can push into my stack, the value of root. Fine. Now the point is, now the case is something like I have an element in the stack, but the current element that I figured out, it is less than the topmost element of the stack. The topmost element of the stack, and I need to just concern about the value of that particular element. So because I am adding the basically nodes into this stack. Now if I just do in that way, in that case, what I need to do, first of all, let me create a new node. Okay, with the value ai, and mark the right child of the topmost element of the stack as that given node, and I can push that given node into the stack. Fine. Okay, even if that is not the case, that in other case, the other case is I have a value, that means ai is greater than the topmost value of this stack. Then in that case, I need to pop out some elements, and I need to just concerned about the edge case as well. If my stack is not empty and the value at the top, it's basically less than ai, we are happy because we don't have given any duplicates in the tree. So we can do in that way. We shouldn't have to handle the duplicacy case here. So we are good with that. Now, if that is the case, then what I just told you, then I need to keep track of the last element which gets popped out. Because that last element will be the left child of that particular element of AI. Isn't it? So if that is the case, then I can make last, and I can update my last as toto, and I can remove I can keep it as null. Okay, now what I can do, I just figured out the last element. So let's first create a new tree node for that particular element. With the value of ai. Now what I can do, the value for that particular node, the left child of that particular node will be my last, and the right child for the topmost element. If let's first check whether we have a topmost element in the stack, or there might be a case that my stack gets empty. So I need to check that thing. If my stack is not empty, then but I need to check whether I need to mark the rightmost child for the top as the given node. If I just do in that way, I will somehow solve this question. Looks like a good approach to me. And I need to return root. Let's again check the way we think and the way we applied the algorithm. Are they both matching or not? Or have we missed any case or not? Let's first check. Okay, what we do in the starting, we just created a stack and which contains all the nodes. Nice. And we just take our n, which is the size of my array. Nice. I just iterating over my array and I'm just checking whether my stack is empty. Because I know that stack will be empty, only in that case I need to push now that element as well. Sorry, I just forgot that thing. Okay, because if that stack is empty, that means this is the first node, kind of. So that means I need to make it as a okay. Oh, sorry. I just need to push. Okay. So that means I can't say that it will be my root. The root must be the topmost element in this stack for sure. But yeah, I need to construct a node here and I just need to add the node if stack is empty because I can't do anything else. And the other case will be if we have our value, it is less than the topmost value, then we are sure that in that case, we need to mark it as our right child for that particular element. So we are doing this thing. So it seems right to me. Now the other case will be if AI is less, if it's not less than, it will be greater. So that means it should be the root of some of the nodes. So I'm just checking out all the nodes. So for that, what I'm doing, I'm just checking up till when I have that given value, it's greater than to the topmost value. So I'm just maintaining my last node because it is required. And what I am doing, I am just creating one new node and just what I'm doing and just mark the left child for that particular node as a last. Nice. If I do in that way, it seems like a good thing. Now let me test. Okay. Oh, sorry. Nice. Let's submit this code. Oh, okay. What's wrong? Let's try to see. Have we done anything wrong here? We have been given the tree as 231. If we have been given tree as 231, first what we can do, what we are inserting 2 here, and it shouldn't be that. It will be the first element. It shouldn't be the last element of this stack. Okay, so I need to maintain the last information. Let's say it as null. Because the way we are maintaining our stack, it's in reverse sorted order. If it is in reverse sorted order, what does it mean? That means the maximum value should come in the front of my stack. And I am popping the element in that a way that if we have a maximum element, it won't be go out of my stack. And it will always be appear in the starting of my stack. So I need to update as this and I need to pop. If I do in that way, then it should work. So, sorry. Why now? I'm updating my last here. Okay, not stacking. Sorry, I'm doing some silly mistakes today. Let's check. Nice, we solved this question. It took us some time, but we solved this question in order of n time. That's good. That's good for us. Okay, let's solve one more question today. Let's solve this question. I don't know what's this. Okay, the question is we have been given 2 binary trees and we need to check whether they are equal or not. Okay, 2 binary trees are considered equal if they are structurally identical and the nodes have the same value. Okay, I need to return 0 or 1 depending upon this. Okay, let's say I have been given this tree and this tree. I just need to check whether both of the trees are equal or not. It's kind of a very simple problem, but I need to check if the both of the trees are equal. That means the node itself will be equal as well as the left subtree and right subtree, both left subtree and right subtree also should be equal. If all those things are fine, then I can safely say that the both of the trees are identical. To solve this question, it shouldn't take much time. Then what I can just first concerned about the edge case, and you can see that this question, this simple question, it's been asked in Amazon as well. So, but the point is, are we handling all the edge cases? Are we come up with a good solution at one go or not? So, what are the edge cases? What will be the edge cases in this question? The basic edge case for this question will be kind of, let's check whether we have been given both the nodes as empty or not. If we have both as empty, both the trees as empty tree, then I can safely return one, because I know that in that case both of the tree are identical. If any of them, if both are not kind of empty, one of them is empty, that means both the trees are not identical, and in that case I need to return 0. So this will be kind of the one more edge case. Now I end up with both the trees such that both the trees has some elements. Now in that case the idea is very simple, but I need to check whether the basically value for both of them are equal or not, and it is equal, and I say that is the left subtree for both the nodes, are they equal or not? Oh, sorry, I need to concern about the left subtree only, and also we need to check whether the right subtree for both the nodes, are they equal or not. If all these three conditions met, then only I can say that both the given tree is identical. Otherwise, both the given trees are not identical. If I just solve in that way, I am done. Sounds like a simple solution to me. Okay. Oh, sorry. Today I'm doing a lot of silly mistakes. Nice. Let's submit our code now. Nice. We got a really good point. गोयल दोनों नॉन नल होने से ट्रू कैसे कह सकते हैं? I didn't say that, Goel, but I just said to you that basically if both of them are null, only then we are saying that as true, because in that case both of the trees are empty. If both of them are non-null, then I am checking. I'm checking all the three conditions. Where the first condition is whether the value of the nodes are equal or not. If both the trees needs to be identical, okay, fine.
Hey guys, in this video we are going to talk about the problems of code drift day 1. The topics are binary trees and tries. So let's get started. The first problem is BST sum. The problem description states that the cost of an array ARR is the sum of all the values in the left subtree of the binary search tree formed by inserting the elements of ARR in the order they appear in it. Find the sum of the cost of all the permutations of length A. Since the answer can be large, we need to return it modulo 10 raised to power 9 plus 7. A permutation of length n is an array consisting of n distinct integers from 1 to n in arbitrary order. The problem constraints are n can vary from 1 to 10 raised to power 5. Now let us discuss the problem with an example. Now let us look at this example. We are given a as 3. That means we have an array of length 3 which have elements from 1 to 3, right? So all the elements are 1, 2 and 3. Now the permutations we can make out of these 3 elements are this one, this one, this one, this one, this one, this one. These are all the valid permutations we can make. Okay. Now we need to create binary search trees out of all these permutations. So let's do that now. So the first binary search tree will be, first we have 1 as the element, then we'll insert 1 here, then we'll have 2. For 2 we know 2 is greater than 1, so it will come to the right of 1. Then for 3 we know that 3 is greater than 2, so it will go like this. From 1 3 is greater than 1, so it will be on right of 1. From 2 it is greater than 2, so it will be on right of 2, so 3 will be here. Okay, now let's talk about second binary search tree. In second binary search tree we have 1 3 2, so first we need to insert 1. After that 3 is greater than 1, so 3 will come on right. Then after that we can see that we have element 2 as the last element, so we need to insert 2 here. Now from 1 I know that 2 is greater than 1, so it must be on the right of 1. Okay, from 3 I know that 2 is less than 3, so it must be on left side of 3, so 2 should be here. So in that way we can create binary search trees. For the third one it will look like 2 1 3. Similarly, in this fashion we can create all these 6 binary search trees. Now the answer to our problem is sum of all the values on the left subtree of each and every binary search tree, right? So the left subtree of first binary search tree, it has nothing on the left, right? So we don't have to add anything to the answer from this subtree. Now again for second one we don't have anything on the left, so we don't have to add anything here again. Now for third binary search tree we can see that we have one value here, so we need to add 1 to the answer. Let's say our answer variable is stored here and currently it is 1 because of this, right? After that fourth binary search tree have 1 in its left subtree, so I am going to add 1 here as well, so the value will become 2 here. Now for the fifth binary search tree I can see that we have 3 on the left subtree, 2 and 1, that is 3, right? Similarly here as well I can see that we have 3 on the left subtree, so I need to add 6 to the answer, so our total answer will be 8. So that is our final answer in this case. Now let us talk about the solution to this problem. Let's say we are given any binary search tree which is rooted at some integer a, right? Now all the values which are less than a should be on the left subtree of this a. Okay, let's say all those values are x, so all these values should be less than a, right? Similarly, what will have on the right subtree? All the values which are greater than a, right? Now from this observation the conclusion that we can draw out is that all the values which are less than a should be present on the left subtree of a, right? So if we have any binary search tree that starts with a and it is some permutation, then I need to add all the values from 1 to a minus 1 to the answer, because all these values will lie on the left subtree of our current binary search tree, right? And as we know, the root of binary search tree is the first element of the array, right? So for each permutation basically I need to add 1 to a minus 1 to the answer, sum of all these values to the answer. Now again let us look at this example and try to solve it using the observation we just made. So for the first element I need to add 1 to 1 minus 1, that is 0, to our answer. Since this range is invalid we don't need to add anything. For this again we don't need to add anything. For this one I need to add 1 to 1, or basically 1 to the answer. For this again I need to add 1 to the answer. For this I need to add all the values between 1 and 2. So I need to add basically 2 plus 1, 3 to the answer. For this one again I need to add 3 to the answer. So the answer of all these permutations will be 3 plus 3 plus 1 plus 1, and that is 8 again, right? So basically what we can observe here, if I know the root of some array, then I can calculate the answer for this array with a simple formula, right? What I need to do, I need to sum all the values from 1 to a minus 1 if that range is valid. Now the next thing that we need to notice is we are given all the elements from 1 to a, which is a permutation. Then let's say I fix the first element to x, then I have to choose rest of the a minus 1 elements, right? So that I can do in a minus 1 factorial ways, right? So if I fix my x, I know that I can choose the rest of the elements in a minus 1 factorial ways. So that basically gives us the contribution of this element to the answer. Now for any element x, the sum of all the values from 1 to x minus 1, it will be x into x minus 1 by 2, and I'll multiply it with a minus 1 factorial, because I can have this permutation a minus 1 factorial times with x as the root element, right? Now let us talk about the code. So our formula was we need to iterate from 1 to a, and for each number x we are using this formula x into x minus 1 by 2, and we are multiplying it with a minus 1 factorial, right? So that is basically what we are doing here. But since we need the answer modulo some number, in this case 10 raised to power 9 plus 7, so instead of dividing by 2, I have already pre-calculated a mod in 2. It is basically the mod inverse of the current number. So instead of dividing by 2, I am basically multiplying by inverse of 2, or 2 raised to power minus 1. Now 2 raised to power minus 1 modulo 10 raised to power 9 plus 7 is stored in this number, right? So now whenever I need to divide, I'll just multiply by this mod in 2. And each time we also need a minus 1 factorial. So we are pre-computing a minus 1 here. Okay, So after pre-computing, what we'll do, we'll run a for loop from 1 to a, and we'll use our formula I into I minus 1. This is divided by 2, right? So that's why we are multiplying with the inverse of 2, and then we are multiplying that value with factorial a minus 1, and then we are taking the mod, and after that we are just adding it to the answer, and then we are returning the answer. So it's quite straightforward. Now let us move on to the second problem. The second problem that we're going to talk about is max base pair, and the prerequisite to this problem is tries. You should know how the tries data structure work. So I'd highly recommend you to learn about tries first. Now the problem description is, you are given an integer array A. There's a function f for two integers x and y with another variable b base, right? Now for calculating the functional value, first convert x and y in base b, and then the ith bit of f x y b will be xi plus yi mod b. You have to return the maximum functional value possible for any pair of elements of array A in base B. Please note that you can take two elements for pair from the same index. Note, array elements are in base 10, and you have to return your answer also in base 10, calculated value from equation in base B. And the problem constraints are, A can vary from 1 to 10 raised to power 6, and each element of the array can vary from 2 to 10 raised to power 6, and the bases can vary from 2 to 9. Now let's talk about this problem with an example. Let's say we are given this example here. We are given an array of length 10, and we are given the base as 3. That means we need to first convert all these elements to base 3. So let's do that first. Now here I have converted each and every element to its base 3 representation. I need to find a pair whose sum is maximum base 3, right? And the sum that we are talking about it, let's say we are given two numbers. Let's say I choose this one 12 and 101. Then how do I need to sum them? I'll write them here 1 2 and 101. So what I'll do, I'll add these two, it will give me 3. I'll add these two, it will give me 1. I'll add this, it will give me 1. Now for each digit I need to again do a modulo by 3. So for 3, if I'll do it modulo 3, it will become 0. 1 modulo 3 will be 1, and 1 modulo 3 will be again 1. So the answer for adding 12 and 101 in this manner I am getting is 110. So that's how we need to add when we are talking about two pairs. Now we need to maximize the answer, right? In this example, we can see that if we take these two pairs, that is 100 and 101, and if I repeat the same procedure that I did here, that is 1 plus 0, that is 1, 0 plus 0 will be 0, 1 plus 1 will be 2. Now doing modulo by 3, it will remain 1, it will remain 0, it will remain 2. So I'll get 201 here. So for this specific case, 201 is the best we can do. Okay, so that's what we need to calculate for any array given to us. And if I convert 201 back to integer, it will be 19. So for this specific case, the answer to our problem is 19. So in this way we need to solve this problem. Now let us talk about the solution to this problem with the same example. So basically I have taken that same example. These elements here, they represent the value of 1 to 10 in base 3, right? So we have b equal to 3 here. So what we can do, basically we need to find any pair which can maximize our sum, right? So the first thing that I'll try to maximize is the most significant bit, right? Let's say we are given some number here, 2, 1 and 6. Now if I'll add 1 here, then I'll get 217. But if in the same number I am adding 1 here, I'll get 316, which is way bigger than 217. So basically the whole concept is, first off we'll try to maximize the most significant bit, and then we'll move on to maximize the second most significant bit, and in this manner we'll go from left to right. Now that we know we need to go from MSB to LSB, let's say we are at some number right now. Let's say it is 101. Let's say we are at last number right now. Then what I'll do, I'll try to find any number which can maximize it. Okay, so what is the maximum I can get at the most significant bit right now? The maximum value that I can make at most significant bit is b minus 1, right? That's what I can make. Currently we have 1 here. Then what is the value x that I will add to this most significant bit so that I can make b minus 1, right? That means I need to add b minus 1 minus 1. Okay, that is x, right? So the first thing that I'll try to search for is, do I have any number which is equivalent to b minus 1 minus 1, or basically b minus 2. Okay, so in our case b is 3, so 3 minus 2 is 1. Do I have any number in the third place which is 1? If we look closely into the array, we can see that we have one candidate here. Okay, the third digit of this number is 1, right? So we have just one candidate here, so we'll put 100 here. Why didn't we go further? Because we have only one candidate, right? But let's say we don't have one candidate now. Okay, let's take one more example here. Let's say we are given these four values which are in base 3 already, and we need to get the maximum pair I can have for each and every value, right? So let's say I want to maximize this 100. I want to find some pair that can maximize it. So what I'll do, I'll write 100 here. Then I'll go from the most significant bit. Okay, so what is the best I can make out of it? That is b minus 1 or 2. B minus 1 is equal to 2 here. Now what is the number I need to add to 1 which will make it 2? So obviously that number is 1, right? So I'll search for the candidates which have 1 on third place. The first candidate will be this one, second will be this one, third will be this one. All three satisfies the condition, right? Now let's move on to the second most significant bit, or this one. Now the second most significant bit is 0. Now again I'll do the same procedure. I'll try to maximize this 0. So what is the maximum I can get at this position? It is again 2, right? So I'll do the same calculation here. What is the value I can add to x that will make it 2? So I'll see that x equal to 2. So I'll try to find among all the candidates that I have selected, do we have any candidate which have 2 at its second place? So I'll see that I don't have any candidates, right? None of them have 2 at second place. Okay, fair enough. That means we cannot make our second digit equal to 2. Now since I cannot make 2, I'll try to make 1 at first digit, right? So what is the value I'll add to 0 so that I can make 1? So that is 1 obviously. Now I'll try to search for a number which has 1 at its second digit. Okay, now out of these three candidates I can see that this one and this one has 1 in its second position, right? Now this candidate is also neglected. So now we have two candidates which is maximizing my value currently, right? Since we have two candidates, let's move on to the last digit. Now again I'll try to maximize my last digit. In order to maximize it, the best I can do is I'll try to make it 2 first. In order to make it 2, I'll try to find the number which have its last digit as 2, right? Now if I look at my candidates, these two, I don't have any of those values, so I cannot make 2. Now I'll try to make 1. Now again I'll check which one of these have 1. So I'll see that my last candidate has 1, right? That means this guy can actually maximize my sum while I'm talking about this 100 value. So in this manner we can solve this problem real quickly. But there is a catch. We need to find these candidates each time, right? For each digit we need to iterate over all these candidates. But we can do it faster by using prefix trees or tries. So let's do that now. So basically if we are given some array, what we'll do, we'll iterate from left to right, and let's say we are currently at this element, ith element. Then what we'll do, we'll try to build a try over all the previous elements, and I'll try to maximize my current element using the try I have built on the previous element. Now let us try to build try over these three values first. Let's say this is the root node of our try. Then the child at each level a try can have is b. Why? Because we can have values at any position between 0 to b minus 1. I'm going to insert this element first. So it has 1. So let's say this is 1. Then again 1. Then let's say this is again 1. Then 0. Let's say this is 0. Okay. Then I'm going to insert this value. Then it will be like 1. Here 1. Then again 1. Now another 1. Right. Now let's try to add this value. It is 1. Then it's a 0. Then it's a 1. Right. Now this is the try structure that I have built right here. Let's say currently I'm at this value. Then I need to find the optimal pair for it, right? So this is my value right now. So I'll start from MSB, that is 1. Now I will try to make it 2 first. Okay, so I'll search for a 1, and in our try we'll see that we have a node which corresponds to 1. So we'll iterate on that, we'll go there, we'll say okay, we are here now. Now from this node, we'll try to check the second digit. Okay, what is our second digit? This is our second digit. We say that we need 2 here. Okay, so from this node, I'll try to search for 2. And from this, we can clearly see that we don't have any node which corresponds to 2, right? We have just 2 nodes. The first one corresponds to 1, the second one corresponds to 0. Okay, so we cannot make it 2. So now I'll try to make it 1. Now we can see that we have 1 here. So I'll go there. Okay, we can make 1. Okay, now that we are here, now I'll iterate on the last digit. So what is the best I can get at last digit? I'll try to make it 2. So I'll search for 2 here. I won't find any 2's, right? We have only 2 nodes, 0 and 1. So again, I cannot make 2 here as well. So I'll try to search for 1. Now we'll see that we have 1 here. So it will go in this direction. So what is the value that I got? I got 1, 1, 1. So again, I got the same pair 1, 1, 1, right? So in this manner, with the help of trie data structure, we can do it efficiently. Now that we got the optimal pair for this element, so we can do it for each and every element of the array by iterating over elements from left to right. So that's how we can solve this problem. For better understanding, let's look at the pseudocode now. Now let us talk about the pseudocode. So let's start off with the solution function. So here is the solution function. We are given an array A and a base B, right? So basically, first we are converting each and every element of the array into its corresponding base B form, and then we are pushing that number to a vector named VEC. After that, we are creating a trie node, which is basically the root node, and we are inserting one element. Why so? Because in order to get a pair, we at least need one element already inserted in trie, right? After that, basically we are iterating from 1 to n minus 1 here, and what we are doing, we are searching for the best element before the current element which can pair up with our current element. So as we have done already it in an example, for 100 this function will return 111. Okay, after that we are combining that and using another vector. So if we combine these two, I'll get 1, 1 plus 0, 1, 1, 1 plus 1, 2, and doing it modulo 3, I'll again get 1, 1, 2, right? So that's what is going to get stored inside this answer vector. After that, I am getting the current answer by converting this digit back to decimal or base 10. Okay, and after that, I am checking if this answer is the best answer, then I'll just insert it into the global answer variable, right? And after doing all these things, I am inserting our current element into the trie data structure. Okay, so in this fashion, we can get the answer, and whatever we get at the end, that will be the maximum optimal answer we can get. Okay, after that, we are returning the answer. Now let us quickly see what these functions do. This first function, it converts a number to its base B form and returns a vector. Okay, and this function right here, it basically converts the given vector back to its base 10 decimal representation. Okay, and after that, we have the standard trie node, and then we have an insert function. In order to understand these functions of tries, you need to understand how actually tries work. And in this function, we are basically iterating over the trie and trying to find the best we can get for our current element. Okay, and this combine, the last function is this combine function. This basically do this operation. It basically adds up both of those vectors and then do the modulo thing. Okay, and then it returns the answer, which is again a vector. So that's pretty much it. And if you enjoyed the video, please hit the like button and do subscribe. Thank you for watching.